In this session, we're going to talk about Hadoop. Hadoop is an open source framework designed for distributed storage and processing of massive datasets. It was built to handle big data challenges like volume, variety, and velocity by using clusters of commodity hardware for parallel processing. For more tech interview materials, please visit our website, baoz8.com. Key components of Hadoop include 1. HDFS, Hadoop Distributed File System. Purpose, a fault-tolerant and scalable storage layer. Data is split into large blocks, default 128 megabytes or 256 megabytes. Blocks are distributed across multiple nodes for parallel storage. Each block is replicated, default, 3 copies across different nodes to ensure fault tolerance. Metadata management. The name node is the master server that keeps track of the metadata, e.g., file to block mappings and replication status. The data nodes store the actual block data and periodically send heartbeat signals to the name node. 2. MapReduce Purpose, a programming model for distributed data processing. There are 2 phases. Map phase breaks the input dataset into smaller chunks, key value pairs. Each chunk is processed in parallel on different nodes to generate intermediate key value outputs. Shuffle and sort. Intermediate results are grouped by key and sent to the appropriate reducer. Reduce phase aggregates intermediate outputs to produce the final result. Fault tolerance. If a task fails, MapReduce automatically reassigns it to another node with the same data. 3. Yarn, yet another resource negotiator. Purpose manages cluster resources and schedules tasks. Resource manager, central component that allocates resources for applications. Node Manager runs on each node to monitor resource usage and task execution. Yarn enables multiple applications, e.g., MapReduce, Spark, to run on the same Hadoop cluster. 4. Hadoop ecosystem tools Hive, SQL-like querying interface for HDFS data. Spark, in-memory data processing engine for faster computations. HBase, a NoSQL database for real-time reads-writes on HDFS. Pig, scripting platform for complex data transformations. Under the hood, here's what happens usually. 1. Data ingestion. A large dataset, e.g., web logs, clickstreams, or images, is uploaded into HDFS. Blocks are replicated and distributed across data nodes. 2. Job execution. A user submits a MapReduce job to process data. Yarn schedules the job, assigns resources, and coordinates task execution. Data processing happens locally on the nodes where the data resides, reducing network overhead. 3. Fault tolerance. If a data node fails, HDFS retrieves data from another replica. Failed MapReduce tasks are restarted on healthy nodes. Example use cases are log analysis, analyze terabytes of server logs to detect trends or errors. ETL pipelines, transform raw data into structured formats for downstream analytics. Genomic sequencing, process huge datasets for pattern recognition in genetics. Retail insights, analyze purchase history to recommend products in e-commerce platforms. Advantages of Hadoop are scalability, easily add nodes to handle growing data. Fault tolerance, data replication and task retries ensure reliability. Cost effective, runs on commodity hardware, reducing infrastructure costs. Open source ecosystem, extensible tools to meet diverse big data needs. Challenges and limitations include high latency, MapReduce is batch-oriented and unsuitable for real-time processing. Complex configuration, requires expertise for setup and maintenance. Storage overhead, replication triples the data storage requirements. Thanks for watching. For more tech interview materials, please visit baoz8.com. In this session, we're going to talk about HBase. HBase is a distributed, scalable, and NoSQL database that runs on top of HDFS. It provides real-time, random read-write access to massive datasets, making it ideal for applications requiring low-latency data operations. For more tech interview materials, please visit our website, baoz8.com. Components of HBase include 1. HBase Master oversees the cluster, assigns regions to region servers, and handles schema operations. Coordinates balancing of data and manages the addition or removal of nodes. 2. Region servers, core workers of HBase, responsible for handling read and write requests. Store regions manage memstores in-memory buffers and serve H files on disk storage. 3. Regions. Tables are split into horizontal partitions called regions. Each region holds a range of rows, and as regions grow, they split to distribute the load across region servers. 4. Write-ahead log. Well, a log file ensuring data durability. Every write operation is first logged in WAL before being written to memory. 5. HDFS, underlying storage layer where HBase persists HF files and WAL logs for fault tolerance and scalability. 6. Zookeeper, central to cluster coordination, ensuring availability and managing metadata like region server locations. How HBase works under the hood. 1. Write path. A write request enters the system. The data is first logged in the WAL to ensure durability in case of failure. Then, the data is written into the memstore, an in-memory data store. Once the memstore reaches a threshold size, it is flushed to HDFS as HF files. 2. Read path. A read request checks the memstore for recent data. If not found, HBase consults the block cache for cached data. If still unresolved, the request queries files stored in HDFS. 3. Region management. Regions grow and are split into smaller regions to maintain balance. The HBase master assigns these regions to region servers, ensuring even data distribution. Example use cases are time series data storage, logs, metrics, and sensor data that require real-time insertion and analysis. Real-time analytics, use cases such as social media trend analysis and recommendation engines. Enterprise applications, fraud detection in financial systems or customer behavior analytics in retail. Event monitoring, applications requiring real-time alerting and event handling, such as network monitoring. Pros are 1. Massive scalability, can handle petabytes of data spread across thousands of nodes. 2. Fault tolerance, achieved through HDFS integration. 3. Low latency, optimized for random reads and writes. 4. Flexible schema, handles sparse datasets with varying column structures. Cons include 1. Complex setup, requires expertise for configuration and optimization. 2. No built-in query language. Unlike SQL databases, querying requires custom code or integration with tools like Hive. 3. High resource demand, memory and CPU intensive, especially under heavy workloads. 4. Dependency on Zookeeper adds an additional layer of complexity and a single point of failure. Thanks for watching! For more tech interview materials, please visit bowsy8.com. Zookeeper is a distributed coordination service designed for managing and synchronizing large-scale distributed systems. It provides a consistent, centralized repository for configuration information, synchronization, and naming services. For more tech interview materials, please visit our website, bowsy8.com. Key components of Zookeeper. 1. Z-nodes, hierarchical data nodes used to store data or metadata. Can be persistent, data retained, or ephemeral, deleted when the client disconnects. Supports versioning and access control. 2. Ensemble, a group of Zookeeper servers, typically an odd number for quorum, working together to provide fault tolerance. One server acts as the leader, others are followers. 3. Leader and followers. The leader processes write requests and ensures consistency. Followers serve read requests and forward write requests to the leader. 4. Clients. Distributed systems or applications that connect to Zookeeper to interact with Z-nodes for configuration, coordination, and status updates. How Zookeeper works under the hood. 1. Read and write requests. Reads are served directly by followers or the leader for low latency. Writes are always processed by the leader to maintain consistency and are replicated across followers. 2. Consensus Protocol ZAB. Zookeeper uses the ZAB, Zookeeper Atomic Broadcast Protocol, to ensure fault-tolerant consistency. Writes are logged and replicated to followers, only committed once a majority quorum confirms. VAR 3. Synchronization. Clients watch Z-nodes for changes. If a change occurs, Zookeeper notifies the client. Watches are lightweight and used for real-time updates. 4. Session management. Clients establish sessions with Zookeeper. Heartbeats are exchanged to maintain active sessions. 5. Atomic operations. Zookeeper provides atomic operations like creating, deleting, and updating Z-nodes, ensuring no partial failures. Example use cases are service discovery. Zookeeper stores the metadata and locations of distributed services, enabling applications to discover and connect to them dynamically. Leader election, used to select a leader in a distributed system, ensuring only one instance performs critical tasks. Configuration management, distributed systems store configuration settings in Zookeeper for consistency across nodes. Distributed locks, Zookeeper provides primitives for locking, ensuring mutual exclusion in critical sections. Pros are 1. High availability. Fault tolerance with ensemble redundancy ensures no single point of failure. 2. Strong consistency guarantees consistent data across all nodes. 3. Lightweight, minimal resource overhead, suitable for high throughput applications. 4. Versatility supports a wide range of use cases from service discovery to distributed locking. Cons include 1. Complexity. Setting up and managing the ensemble requires expertise. 2. Write bottlenecks. Writes can become slower due to quorum-based replication. 3. Scalability limitations. Not designed for extremely high read-write workloads, better suited for coordination tasks. Thanks for watching! For more tech interview materials, please visit bowsy8.com. Apache Hive is a data warehousing tool built on top of Hadoop for querying and analyzing large datasets using SQL-like syntax called HiveQL. For more tech interview materials, please visit our website bowsy8.com. Components of Hive include 1. Metastore, stores metadata about tables, columns, partitions, and data locations. Uses relational databases like MySQL or PostgreSQL. 2. Driver, acts as a controller, managing query execution, parses, compiles, and optimizes queries. 3. Query compiler, converts HiveQL queries into execution plans with MapReduce, Tez, or Spark jobs. 4. Execution engine, executes the query plans and coordinates with Hadoop's processing frameworks. 5. HiveQL, the query language used to interact with data stored in Hadoop. Under the hood, 1. Data storage. Hive tables map to data stored in Hadoop Distributed File System, HDFS, typically in formats like Parquet, ORC, or CSV. 2. Query execution. HiveQL queries are submitted to the driver. The query compiler translates the queries into logical plans optimized for execution. The execution engine converts these plans into tasks, MapReduce, Tez, or Spark jobs, and runs them on Hadoop. 3. Partitioning and bucketing. Partitioning divides data into smaller segments for efficient query execution, e.g. by date. Bucketing further divides data into buckets for better performance during joins or aggregations. Example use cases are data warehousing, ETL pipelines for structured and semi-structured data, reporting and analytics on large-scale datasets, business intelligence, running ad hoc SQL-like queries on petabyte-scale data, log analysis, processing and querying application or server logs stored in HDFS. Pros are 1. SQL-like syntax, easy for users familiar with SQL. 2. Scalability, handles petabyte-scale datasets using Hadoop. 3. Flexibility, supports various storage formats, Parquet, ORC, and execution engines, MapReduce, Tez, Spark. Cons are 1. High latency, queries may have significant latency compared to real-time systems. 2. Dependence on Hadoop, tight coupling with the Hadoop ecosystem. 3. Complexity, requires expertise to optimize queries and manage partitioning. Thanks for watching! For more tech interview materials, please visit bowsy8.com. Redis is a high-performance, in-memory key-value store used for caching, message brokering, and more. For more tech interview materials, please visit our website, bowsy8.com. Core components include 1. Data structures. Redis supports various data types, strings, basic key-value pairs, e.g. storing user sessions, hashes, maps of key-value pairs, e.g. user profiles, lists, ordered collections, e.g. task queues, sets, unordered collections of unique elements, e.g. tags, sorted sets, sets ordered by a score, e.g. leaderboards, bitmaps, and hyperlog logs, optimized for specific use cases like analytics. 2. Persistence. Redis stores data in memory but supports persistence through RDB snapshots, saves the entire dataset at intervals. AOF, append-only file, logs every write operation incrementally for recovery. 3. Replication, implements a master-slave architecture for read scalability and fault tolerance. 4. PubSub, messaging system for real-time communication between applications. 5. Cluster mode allows sharding and distributing data across multiple nodes for scalability. 6. Eviction policies. When memory limits are reached, Redis uses policies like LRU, least recently used, LFU, least frequently used, or no eviction. What happens under the hood? 1. Command processing. Redis operates on a single-threaded event loop. Commands are processed sequentially, ensuring simplicity and avoiding race conditions. 2. In-memory storage. Data is stored in RAM, enabling lightning-fast reads and writes. Disk-based persistence is optional for backup and recovery. 3. Replication. Master nodes replicate changes to slave nodes asynchronously. This ensures high availability but may have eventual consistency. 4. Cluster management. Data is partitioned using consistent hashing. Redis cluster mode ensures automatic rebalancing and failover. 5. Data durability. On restart, Redis can restore data from RDB snapshots or replay AOF logs. Example use cases are caching. Example, storing API responses or session data to reduce database load. Benefit, millisecond latency for frequent reads. Real-time leaderboards. Example, gaming platforms tracking player scores using sorted sets. Message queues. Example, using lists or pub/sub for lightweight inter-service communication. Rate limiting. Example, API gateways use Redis to track and enforce request quotas. Geospatial queries. Example, location-based services leveraging geospatial data types. Pros are 1. High performance. In-memory design enables sub-millisecond latency for reads and writes. 2. Versatile data structures, optimized for a wide range of application needs. 3. Simple deployment, easy to set up and use with a small learning curve. 4. Persistence options, combine speed with durability when configured. Cons include 1. Memory dependency, limited by available RAM, which can make scaling expensive. 2. Single-threaded model, may bottleneck for CPU-intensive tasks. 3. Lack of advanced querying, designed for key-value operations, not complex queries like SQL databases. Thanks for watching! For more tech interview materials, please visit bowsy8.com.